This talk is the unreasonable ineptitude of deep image classification networks. This research has been sponsored in part by the DARPA Explainable AI program. The title of this talk comes from a couple different sources. One is a blog posting by Andrej Karpathy, who's now the chief of AI at Tesla. And Karpathy wrote about recurrent neural networks, but he was really referencing an older paper by Wigner, The Unreasonable Effectiveness of Mathematics in Natural Sciences. But if you read the blog posting carefully, he uses many of the same examples that Shannon used when first describing information theory in the 40s and 50s. And so, in a way, Karpathy is arguing that deep networks are having the same influence as mathematics and information theory. And that sounds bold, but he really very well may be right. However, when we started looking at these systems and trying to see how they work, we got the exact opposite impression. Instead of effectiveness, we saw ineptitude. And it reminded me of this book by Samstag called The Uses of Ineptitude, or How Not to Want to Do Better. And Samstag was arguing that for people, we should stop wasting our time doing things that we're not very good at and really focus on the things that make our lives better and that we can excel at. That really is the story for image classifiers as well. So I'm going to be talking about image classifiers here. If you don't know what that is, an image classifier is a piece of software, usually now typically built with a neural network that can process an image like this and give a set of human readable responses. So here's a pretty typical answer to this hammer. These are the top responses: product, hardware, tool, knife, and eventually hammer. Hammer is the sixth most common label that this AI gives. And so this is what I mean by ineptitude. Not all of the answers are technically wrong, but none of them are right. And if you get six guesses to get the answer right, that's not very good performance. So the approach I'm going to be using today is I'm going to examine how both humans and AI do at classifying a common set of tools. We're going to look at the errors that both make, and especially the expectations that humans have about how the AI will do, and describe a little bit about the mismatch. To do this, we selected a set of 50 images of 10 common tools, 5 examples of each. Next, we picked a bunch of transforms of the images that based on what we call a principle of invariance. And all of these images and actually the results of the model are available at this URL you see at the bottom of the screen. The transforms were selected with the invariance principle, which basically states that a transform that does not impact information critical for processing will have no impact on recognition. And so for humans, we picked, there are a lot of known invariants like this, like pose, rotation, line drawings, context, and these types of transforms typically don't have a large effect on human recognition. On the other hand, a transform that impairs AI may indicate that it distorts information the AI is using for that classification. We looked at 6 different AI systems to do this: Watson, Google, Amazon, and Clarify, plus 2 custom ones built on the Inception engine, which is also created by Google. The Inception engine allows you to train on a very specific set of answers. The others each know more than 1,000 labels, and so they're very general purpose. We also did a custom trained model that we focused on specifically on training with the same transforms that we're testing on. Here are just some examples of performance of, in this case, the Google model. The upper left is what we saw before. But here's what happens when you do some transforms. The lower left transform is the sketch transform, and it completely subverts the ability of the model to know what it is. It now thinks it's a drawing, hand, angle, sketch, or artwork. And although many of these are kind of correct, it's not really what we're looking for. On the upper right, we see that just putting this framing of leaves completely distorts its ability to know what it is. It now thinks this is grass and nothing else. And another look at this invariance principle, you can see that this bottom right panel, which is we call a splice operation, takes the pieces and breaks them apart and rearranges them a little bit. You might expect that if the AI is using shape, this could distort its ability to do recognition. However, in this case, it's not really impaired. The answers it gives are almost the same as the changed image, which may really indicate that the AI doesn't use shape. And this is something that humans use universally, but the AI may not be using shape and may be using a much more myopic look at the image. Before I show you the results, we also conducted a human experiment. We used 50 participants that took part in 3 complementary tasks. One is they did the same type of tasks that the AI did. They saw pictures and classified them. They also gave ratings. We showed them an entire page of transform images and gave a rating on a scale of how difficult they thought the AI would have on those images. They also, for a page of transforms, picked out the cases they thought would have the most difficulty or pose the most difficulty for the AI and gave text-based descriptions of why they thought the AI would have difficulty. Here are the results. Now, for the AI, it always has its best answer, and we can score if it got it correct by whether the best answer was correct, and that's what the middle panel shows. You can also give a more lax scoring where if anything above some threshold that it returns is correct, you call it correct, and that's what the right panel shows. And performance in some cases was a little better, but still pretty abysmal. You can see that the 4 lines on the left are the 4 general purpose models, and this is what we mean by inept. Even for the untransformed images, performance was at most about 50%, and most of the models didn't do that well. Even the simplest transforms impaired accuracy substantially and catastrophically, transforms that have no impact on people. This includes things that retain shape by just turning things black and white, or focus on the shape by using edge detection. The pink shows the human performance, and there's no errors of any errors of any substantial amount to remark on. People were almost perfect in this task, 98 to 99% correct on average. The 2 middle lines show the custom trained model that only knows the 10 tools. And here we see a set of transforms that are pretty highly accurate, above 90%, 4 or 5 that are pretty high. But then for other transforms, accuracy starts to go down. The model trained to understand the transforms does better than the one that isn't, which may give an avenue to make more robust models in the future. So overall, that looks like the AI is not really anywhere near as capable as humans. The error rates are 10 to 20 times to 100 times higher than humans are, and so we see substantial problems with the AI. So think about these errors. We asked people to predict which transforms do you think are going to be the most difficult by having them rate each type of transform individually. Humans' expectations did not predict any of the general purpose models and only predicted one of the inception models at a significant level. Nevertheless, that correlation was about 0.2, which was not very substantial. We also had them pick out specific cases, and so we correlated the number of cases they picked out for any transform with the accuracy of each AI in that transform. Here it was somewhat correlated with a number of models, but not highly correlated, so people maybe were able to pick out more for the untransformed images than for the transformed images, and that's sort of what picks up a correlation. Only Inception A again produced a reasonable correlation. But what's interesting is that the thing that produced the highest correlation is when we looked at the number they picked correlated with the response time to classify those images, and that was an independent measure. And so it's as if they're picking out things that to them are difficult based on that they take them longer to resolve or figure out what the thing is. This is what we call cognitive anthropomorphism. Their expectations are about what's difficult for them and not necessarily what's difficult for the AI. We also looked at the types of errors that the AI made and the types of errors people expected. So the left shows the types of errors the AI made. We looked at 2 classes of tools, the wrenches and the scissors, and looked at the types of errors and coded these. Many of the errors had to do with properties, like the material the thing was made up of, metal or wood, or the color, if it was green or red or blue. There was also a lot of errors that had to do with distractors, mostly with the framing. So it would say something in the background rather than the thing you're looking for. There was a set of errors related related to class level errors, holonyms, hyponyms, meronyms, and hyponyms, which are about saying things like tool instead of hammer, or components of a component of the thing instead of the whole. There's also meta descriptions. These are saying sketch or drawing instead of what it's about. And then there are a few other sort of errors that are a little harder to characterize and are more general. So in contrast, we also asked people to describe what they thought the AI would have difficulty with, and we coded these. We had two coders, and I'm just showing you sort of the ones that both agreed with category and ones that either agreed with. People did pick out a lot of attention or distraction codes, which is similar to the errors that the AI made. But other than that, there wasn't a lot of anticipation of the type of errors that the AI made. Now, people picked out a lot of visual properties, resolution, pixelation, figure ground, or figure ground segmentation, and things like that, which are things that are problematic for people. And they may have been problematic for the AI, but these were not how the errors were manifested. And so many of the types of ways errors were manifested in the AI are not anticipated by people's expectations. In conclusion, we have some lessons for potential users of image classifiers. One is that no general purpose classifier seems to be very good, and the uses of an ineptitude lesson really applies here. Also, AI doesn't seem to appear to use shape very much. There's also some things to think about for human expectations. We see that users mainly expect errors that are similar to their own limitations. This is cognitive anthropomorphism of AI. These sometimes match AI, but the AI mistakes are usually of an entirely different nature. Only the distractor mistakes were really anticipated by humans. And we just hope that this research can help maybe make better AI systems and make better systems that allow people to interact with AI in a more interesting and intelligent way. Thank you.